Section 4.7, Optimization Problems. Suppose a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fencing along the river. What are the dimensions of the field that has the largest area? Let's try drawing this. So let's say here's the fence. We don't need any fencing along the river. Even though the river is straight, it probably is a little bit like rivery. Okay, so then let's come up with some variables to represent the dimensions of this field. So we could say that this could be x and this could be y. Since it's a rectangle, that means this is also x. We don't care about the part near the river, and the entire thing has an area of A. So because it's a rectangle, the area A is x times y. So we would like to maximize this. However, right now it's not a function of x or a function of y. It's got two variables in it. So we have to find some way to eliminate one of the variables. So they told us that the farmer has 2,400 feet of fencing. So let's use that information. That means that if I go from x and I add y and then I add x again, that has to equal 2,400. So it's the same as x plus y plus x is 2,400. Otherwise, 2x plus y is equal to 2,400. So I can solve for one of the variables. How about we solve for y? This means that y equals 2,400 minus 2x. Since we know what y is now, we can eliminate it. So we return to our area equation, which was x times y, and we eliminate y by plugging in for what we solved for it. So it's x times 2,400 minus 2x now. So we distribute, and we get 2,400 times x minus 2x squared. Now we can write this as a function of x. So a of x is 2,400 x minus 2x squared. And notice x, the smallest it could possibly be is 0. We can't have a negative value for this side length. But the biggest it could possibly be is 1,200. Because if this is 1,200, then the other side is 1,200. And then together that's 2,400 and y is 0. Y can't be a negative value either, so there's no way that x can be more than 1,200. So this means that we have a closed domain from 0 to 1,200 for x. Since we now have a function of x, we can take the derivative in order to maximize this function. So we take a prime by the power rule. Oops, I forgot my x over there when I was rewriting this thing. Let's put that back so that I can get rid of it. So it's 2,400 minus 4x. And I want to see when this equals 0. That's when we have a potential maximum, because I remember on a closed interval, our maximum occurs at either one of the endpoints or at a critical number. So solving this equation tells me that x must be equal to 600. So I have to check my endpoints at 0 and at 1,200. So I check at 0 and I plug it in for x. I get 0 over there, so the area is 0. If I plug in 600, then I get an area of 720,000. If I plug in 1,200, that's my last endpoint, then again I get an area of 0 because the y value becomes 0. So let's calculate what the dimension is over here, because this is definitely our maximum. Well, we know that y is 2,400 minus 2x. So it's 2,400 minus 2 times 600 at the maximum. So that's 1,200. So it looks like we should make this field 600 feet by 1,200 feet to maximize the area. Say a cylindrical can is to be made to hold 1 liter of oil. Let's find the dimensions that will minimize the cost of the metal to manufacture the can. Well, drawing this cylindrical can is a challenge, of course, for me. So let's see if I can do it anyway. Okay, not my worst can, not my best can. Let's say that the radius is right over here. And let's say that the height is over there. So we'll call the radius of the can r and the height of the can h. So these are the dimensions of the can. We need to find the dimensions that minimize the cost of metal to manufacture the can. So the metal is only going around the outside of the can, so that's the surface area. So for the top and bottom, those are 2 circles, so those have an area of pi r squared. So that means that the surface area will have 2 pi r squared in it for the top and bottom. Then we need to see how much it is around the can. Well, if I unroll the entire part of that can, then it'll have a height of h, and it'll become a rectangle, and the top part is this part over here. That's the distance around the circle. You could think of it as the perimeter of the circle, or the circumference, which is 2 pi r. So that means that the area will be 2 pi r h around the can, so the total surface area is 2 pi r squared plus 2 pi r h. Again, we have the issue where we have r and h. We need to eliminate one of these. Well, we know that the can is designed to hold 1 liter of oil. In order to try to break that down into something cubed so that we can have individual units for each of our r and h, we should probably rewrite that as 1,000 cubic centimeters. So the volume, which is pi r squared times height, the circle at the base stacked up, we can say is equal to 1,000 cubic centimeters. Solving for h gives us that h is equal to 1,000 divided by pi r squared. So now we can go back in and eliminate h. So we get that the area is 2 pi r squared plus 2 pi r times h, which is 1,000 over pi r squared. We can simplify that and get that it's equal to 2 pi r squared plus 2,000 over r. So now we have a function of r, function of one variable, and we can minimize this. So 2 pi r squared plus 2,000 over r, and in this case the restriction in r is that it just has to be positive. So let's take our derivative. Well, that's 4 pi r by the power rule minus 2,000 over r squared, because you write that as 2,000 r to the minus 1. And this ends up becoming 4 times pi r cubed minus 500 over r squared. So let's see where our derivative is 0 or undefined. So a prime of r, remember r starts at 0, so we'll start at 0, and oops, this is not x, this is r this time. And it looks like we will have a root, well, we're not going to plug in 0 to be undefined because our domain does not include 0, it starts above 0, so we'll only look at where the numerator is 0, which happens at the cube root of 500 over pi. So if we go to the left of that, then this thing will be negative. If I go to the right of that, then this thing will be positive. So that means that we go down and then up. We're decreasing, then increasing. This tells us that we have to have a local minimum at the cube root of 500 over pi. But we want to know the dimensions that will minimize the cost, so we want to find the absolute minimum. Well, notice that this thing is going, it starts at 0, right? So it starts at 0, then it goes down, hits this minimum, and then it goes up as r goes to infinity. So on this interval from 0 to r, even though it's not closed, there's no other way we could have any other minimum value smaller than the cube root of 500 over pi. So in this case, the local minimum actually will be an absolute minimum. So we have an absolute minimum at cube root of 500 over pi. Let's see what h is so that we can get the other dimension. So h is 1000 over pi r squared. So that's 1000 over pi times 500 over pi to the 2/3 power. So that's the same as 2 times the cube root of 500 over pi. So that's 2r. Okay, so that's the diameter. So that means the minimum dimensions are when the radius is this, and the height is the diameter. In the previous example, we saw that we can actually test for absolute extreme values, not just local ones. So if we have our derivative positive for all of x values less than c, and the derivative negative for all x values greater than c, then we have an absolute maximum. So that means that it's rising the entire time, up until it hits that maximum, and then it decreases the entire rest of the time. Then there's no other way it could have been anything else but an absolute maximum. And the same thing in the other case, the way that we argued before. If it's going down the entire time and then up the entire rest of the time, there's no way it could be anything else other than an absolute minimum. So let's find the point in the parabola y squared equals 2x that is closest to the point 1, 4. So we have our distance formula, d equal to square root of the difference in the x values, x minus 1 squared, plus difference in the y values squared, y minus 4 squared. We would like to eliminate one of these variables, so we have a function of one variable. So notice they told us that y squared is equal to 2x, so that implies that x is equal to half y squared. We solve for x instead of y because that way we don't have to worry about plus or minus when we take the square root. So we take this x value and we replace all of the x's with it to eliminate x. So instead of x minus 1 squared, it's half y squared minus 1 squared plus y minus 4 squared. Minimizing this to find the closest point to the point 1, 4 is kind of a pain because of the square root. So you have to notice that if we have a function d of y and it has some minimum value, let's say dA, then at this x value a, the value of the function d of a is less than or equal to every single other value of the function. So d of a will be less than or equal to d of y for all values. So if we square both sides, we see that d of a squared must be less than or equal to d of y squared, which means that this d of a squared is a minimum value for d of y squared. So that means that we could find the minimum value for the original function if we look at the minimum value of the squared function. They will occur at the exact same x value. They both occur at a. So instead of looking at d with that stupid square root, how about we look at d squared? So let's make that our function, f of y. Then that is just half y squared minus 1 squared plus y minus 4 squared, which is much easier to minimize The minimum won't be the same as the minimum, like it'll be squared instead of, the original, but the x value will be the same. They'll both have an x value of a that forces the minimum. So if we want to switch back to the other minimum, we can always just take the square root. Let's look at our derivative now, try to minimize this. So this is 2 times half y squared minus 1 times y by the chain rule, plus 2 times y minus 4, and that simplifies to y cubed minus 8. Let's see where this is positive, negative. So our derivative, it looks like, has 0 at 2. Right, you plug in 2 cubed, so let's put y over here. If we go smaller than 2, we'll subtract more, so it'll be negative, so it's going down over there, and then bigger than 2, it'll be positive. So by our first derivative tests for absolute extreme values, this implies that there is an absolute minimum at y equals 2. Because it goes down until it hits 2 and then goes up, and it never has any other chance to escape anywhere else. Alright, so now that we've found the absolute minimum y value, let's find the corresponding x value. We know that x is equal to half of y squared, so that's half 2 squared, which is 2. So we now have our closest point. And it is 2, 2. If we look at a graph of this, it looks something like this. So we have nice x equals parabola. And let's say here's 1, 2, 3, 4. Here can be 1 over there. So here's the point 2, 2. And you can see it makes sense. That'll be the closest point to, say, over here, 1, 4, for y squared equals 2x. A man launches his boat from point A on a bank of a straight river 3 kilometers wide and wants to reach point B, 8 kilometers downstream on the opposite bank, as quickly as possible. He could row his boat directly across the river to point C and then run to B, or he could row directly to B, or he could row to some point D between C and B and then run to B. If he can row at 6 kilometers an hour and run at 8 kilometers an hour, where should he land to reach B as soon as possible? So you might say he can run at 8 kilometers an hour. Why doesn't he just go straight through over here and then run the entire rest of the way? Well, he saves a lot of distance if he goes diagonally. The issue is that by saving that distance, it costs him speed, because he can't row as fast as he can run. So it makes sense there should be probably some sweet spot somewhere where he minimizes his time between rowing and running. So let's try to take a look at the distance between D and B, this distance. Well, the distance between D and B is equal to 8 minus x. So this distance over here between A and D, if this is x and this is 3, then I can use Pythagorean theorem. 3 squared plus x squared is this distance squared, so I take the square root. So it's the square root of x squared plus 9. Okay, so now I know what this distance is. I know what this distance is. That's the distance he's got to travel by rowing and by running. So let's come up with a function here. We know that time is equal to distance over rate, because distance equals rate times time. So we can come up with a function t of x, equal to the time that he spends rowing plus the time he spends running. So that'll be the distance spent rowing. That's x squared plus 9. So that's this part. And we have to divide by rate in order to get time. You can row at 6 kilometers an hour. So this is the time spent rowing. Plus, now we need the time spent running. So that'll be the distance running, 8 minus x, over 8, the speed at which you can run. Okay, notice that the x value over here, the smallest it can be is 0. The biggest it can be is 8. So we have a closed interval from 0 to 8. Let's take our derivative now. T prime of x. We can do the chain rule, get that it's x over 6 rad x squared plus 9. And then the other part becomes minus 1/8. Let's look for where this equals 0 to find critical numbers. So let's add 1/8 to both sides. So x over 6 square root x squared plus 9. And let's say this is 4x equal to 3 square root of x squared plus 9 by multiplying both sides by square root of x plus 9 and then simplifying the 6 and the 8 to be 4 and 3. So we get 16 x squared by getting rid of the square root equal to 9 times x squared plus 9. So we divide by 9. Actually, no, let's keep the 9. How about we distribute the 9, and then we get 81 and we get 9x squared. So we subtract 9x squared and we get 7x squared equal to 81. And now we divide and take the square root, so we get x is 9 over rad 7. Notice we don't get the minus because x started at 0. Okay, we have to check, we have a closed interval, so let's look for the value at 0. We know that if we plug in 0, we'll get 1.5 for t. If I plug in 9 over root 7, then I get 1 plus root 7 over 8, which is about 1.33. And if I plug in the last point in our interval, I get rad 73 over 6, which is about 1.42. So it looks like inside of our interval at 9 over rad 7, that'll be our minimum, so we can get there the fastest. So 9 over root 7 kilometers is where he should land. So that's about 3.4 kilometers. So that's how far he should go along the bank to make sure that he gets through the fastest. Let's find the area of the largest rectangle that can be inscribed in a semicircle of radius r. So here's our semicircle. Nope. And here's radius r. So this is minus r. And we want to inscribe a rectangle. So that means the rectangle should have points that touch the circle. Let's say that the height of the rectangle is y, and we could say that this point is x comma y, so that would make the length equal to 2x. So let's say this length is 2x. Okay, so we want to take the largest area, so we want to maximize 2 times x times y. I want to eliminate one of these variables though. Remember that in a circle we have x squared plus y squared equals r squared. So that implies that y is equal to the square root of r squared minus x squared. And you might be saying something at this point like, okay, that's not super helpful. Now I've got another variable, r. But in this case, r is not a variable. R is a value that we just chose. We want to have a semicircle of radius r. R is not changing here. We're taking the box and we're making tons of different boxes to try to see which one has the biggest area. But we never actually change the circle as we put different boxes inside of it. The radius of the circle stays constant once we decide the semicircle of radius whatever that we want to actually do this for. So even though we're using a letter to represent it, r is a constant in this case. It's not changing. So it's not really a problem. This will still end up being a function of x. So we have 2x times the square root of r squared minus x squared. So as a function of x, that's 2x rad r squared minus x squared, where x goes from 0 to r. Right? Because if x is over here, it's a little bit smaller than r, it looks like. But if x goes all the way to the end with a y value of 0, then that would be equal to r. Let's take our derivative. So we get 2 times the square root of r squared minus x squared minus 2x squared over the square root of r squared minus x squared. We can simplify that and get 2 times r squared minus 2x squared all over the square root of r squared minus x squared. So we would like to know when this equals 0. Well, if that equals 0, that implies that 2x squared is equal to r squared. That's how our numerator cancels and gives us 0. So solving for x tells us that x is r over the square root of 2. Let's check now. We have a closed interval from 0 to r, so we can look at a of 0. See that that's 0. We can look at a of r over square root of 2 for a critical number. So plugging in, we get 2 times r over rad 2 times the square root of r squared minus r squared over 2. So that's r squared. And then if we plug in r, we get 0. Because r squared minus r squared would be 0, so y will become 0. So it looks like this is where our maximum will be. R squared is the maximum area. Even though we solved this problem with calculus, calculus was not the only way to solve it. We could have actually just used trigonometry. So let me show you. Let's say that we were to redraw this. So here's a semicircle now. And we're putting the rectangle inside. So we could draw the radius over here with an angle theta over here. The side then over here would then be r cosine theta, and the height would be r sine theta. Kind of like on the unit circle, but with a radius of r instead. So then we could have a function of theta. A of theta, the area, would be, for the rectangle, it would be this entire length, which is 2r cosine theta, times the height, r sine theta. We multiply through, we get r squared times 2 sine theta cosine theta, which we can rewrite because 2 sine theta cosine theta is sine of 2 theta. So that's r squared sine 2 theta. Notice that the biggest that sine could possibly be is 1. So that means the biggest the area could possibly be is r squared times 1, which is r squared. And that happens when this over here is at pi over 2. So theta would have to be pi over 4 to get to pi over 2 if you multiply them by 2. So this thing is maxed out at theta equals pi over 4. So even though calculus is super useful for doing a lot of these problems, it's not always completely necessary if you can think of another trick to solve your problem. Let's take a look at a couple more definitions. If P of X is the price per unit that a company can charge if it sells X units, then P is called the demand function, or price function for P. If X units are sold, then the total revenue, R of X, is the quantity times the price, which is X times P of X, and is called the revenue function. The derivative R prime of the revenue function is called the marginal revenue function, and is the rate of change of revenue with respect to number of units sold. If X units are sold, then the total profit is P minus R minus C, where C is the cost function and P is called the profit function. Notice this is a capital P for profit, and this was a lowercase p for demand or price. The marginal profit is P prime, derivative of profit. So say a store has been selling 200 flat-screen TVs a week at $350 each. A market survey indicates that for each $10 rebate offered to buyers, the number of TVs sold will increase by 20 a week. Let's find the demand function and the revenue function and see how large a rebate the store should offer to maximize its revenue. So how about we let X be the units? So let X be the number of TVs. Oops. That are sold per week. Okay, so we want to know the demand function. So remember, the demand function is $350. It's going to be the price per unit, starting at $350, minus however much we rebate these things. So we should know the rebate is based on the number of additional units past 200. So that means that X minus 200 is something we'll need. That's the increase in sales. So that's all of the additional units past the 200 that they've been selling so far. So for P of X, that's 350. So the price per unit is 350. But then the price per unit gets discounted by $10 because of the $10 rebate. And the $10 rebate applies to all of the additional units, so all of the X minus 200 over. However, it only applies, the market survey says the number of TVs sold will increase by 20 a week. So that's so the $10 only applies to each 20. So it doesn't apply to all of the X minus 200. It only applies to every 20 of them, so we have to divide by 20. Simplifying, we get 450 minus half X. So that's our demand function, our price function. Let's get the revenue function now. So that's X times our demand function. So that's 450 times X minus half X squared. Let's get the derivative. Because we want to maximize revenue, so we get 450 minus X. Well, let's look for where this thing is 0. Clearly that's at 450. If you go below 450, then it's positive, and if you go above 450, then it's negative. So we have an absolute maximum over there by the test that we did before. So that means that P at 450, which is 450 minus a half times 450 equals 225, is an absolute max. For revenue, that is. So that's how much we should price the units in order to make the most revenue. We want to know how large a rebate they should offer. So the rebate is the difference in the original cost, which is $350, and the new cost, the discounted price, which is $225. So they should offer a $125 rebate.